Okay, so I want to talk about universal algebra done in the context of enriched category theory. And with that I mean something more in the classical starting point of Birkhoff, so with recursively generated terms and equation. So let's start from the classical case. Then I will tell you what's going to happen in the enriched context. Okay, and all of this is joined with Jerzy Rosicki. There is a preprint on the archive. So what's universal algebra ordinarily, or equational theories? We deal with languages, which we call PEL, which are just sets of elements that we call function symbols, and they have a arity, which is a natural number, or maybe a finite set. And given a language, we consider structures of that language. What are those? They're just sets together with an interpretation of each function symbol. So a map from A here into A for each f as intended. And out of this, then one following Birkhoff, one builds function, one builds terms. And what are these? These are generated by variables, function symbols, so everything in L is a term, and superposition. And so if you give me n terms, sigma 1, sigma n, and then an term t, I can do t of sigma 1, sigma n. And okay, that's all very nice. And then one considers equations between terms of the same arity, and models of those equations are structures for which the interpretations coincide. Okay, so that's like the logic point of view. And that has been understood category theoretically very well from the very beginning, thanks to essentially Lovier and Linton. So we can say the following are equivalent for a category K, and the first is K can be presented this way, so it's the category of models of an equational theory, like that, in some language, where E is just a collection of equations. And then there are the purely category theoretical understandings. K is the category of algebras for a Ferrari monad and set. That's the contribution by Linton. And then, I guess we all know about Lovier theories. So K can be written as the category of finite product preserving functors from T to set out of a Lovier theory. Okay, and that's there is more, of course, but if you want, this is what made the theory so fruitful category theoretically. And now let's move to the enriched context and see what happens. Okay, so fix V as symmetric, monoidal, closed, locally parametric, presentable as a closed category. Whatever base of enrichment you might want, so should have a tensor product, and for this talk it needs to be locally parametric presentable in the sense of Kelly, but it could be, you can consider regular cardinals and so on, but for today let's say simple. And anyway, so consider abelian groups, or what John was talking about, or cut, or whichever base of enrichment you prefer. Okay, and what do we know in this context? Always staying into the finitely setting. The following are equivalent for AV category K. One, let's leave it empty, otherwise this talk doesn't make sense. 2 and 3 are the obvious generalizations. So K is the algebras, the definitive algebras for a monad. T of V, which is planetary. And 3K is the capital models of Alvear theory in the enriched sense. So T now is enriched theory. Where now this means presents finite powers rather than finite products. And this equivalence was proved by Bauer. And then the theory, from this point of view, was expanded a lot in the enriched context with works by Kelly, Luck, Bork, Gardner, Lucian Wright, and Parker. But most of the work stayed focused on these aspects, but not trying to fill in this gap with some kind of definitions that remind us of the classical approach, because that will make very easy to find examples. And so let me say, what do we know about this and what's my contribution, because it's his contribution on this. Okay, so to fill that gap, we need to talk about a certain notion of language and a certain notion of term. And the languages, there is nothing new. Well, with respect to this, yes, but they have been around in the literature. And the idea, which goes back to Linton, is that realities, instead of being the natural numbers, are the finitely representable objects of your category. So a language over V for me will be a set of things that I will still call function symbols, but they come together with two realities, which are finitely presentable objects of V. And the idea is that this is an input arity, this is an output. Well, you could think of this in the earlier setting as Y being the trivial one, so that there is a 1 here. And you only need that because everything is a coproduct of 1 for set, but that might not be true in V. Okay, and so a language is just a set of these things, and I should have introduced a notation there, so let's put it here. The V is symmetric monadal closed. I will denote the internal one this, like this, just because it makes more sense in comparison to the organized set. So now an L structure is what you can imagine, is simply an object of V together with maps Fa from A to the X into A to the Y for any F like this in the language. Okay, and as I said, this notion of language is not really new, it's been around. And in fact, in a recent paper, Lucian, Wright, and Parker considered, in a much more general context than this, but they consider a similar notion of language, and then a notion of term between this language, which then you can define equation interpretation, which would fit into the framework of this, so proving the equivalence. And a term in that setting would be, in some sense, a morphism in the enriched Lovell theory generated by this. So we have a V category of structures, which with a forgetful factor into V and a left adjoint. So if you want a term in the sense is a morphism like this. Which makes sense because if we go back to the ordinary setting, that's just a tuple of terms in the classical sense. So it's very reasonable. However, what we wanted to do here is give a more elementary notion of term, which can be constructed with very easy steps. Well, this you need a transform construction that defines your free algebra. So in some sense it might be not very manageable. So okay, what's our notion of term? Given a language. So they will be generated by these rules that I'm going to write. One, every map G from Y to X in VF, let's say, is a term of variety XY. What does that mean ordinarily? So I said that, again, let's keep a side for that. In the ordinary setting, it's enough to consider Y to be 1. So I'm telling you that given any map from 1 to n, which is just specifying a number less or equal than n, I'm telling you that there is an n-ary term specified by this, which is just a projection from n variables into the k variable. So in the ordinary setting, this is just, if you want, variable declaration, the fact that you can choose them. But I will say something about this later when we see some examples. 2, which shouldn't be surprising, if f is in L, then f is a term of the same arity, and that's like in the ordinary setting. And again, 3 is a generalization of superposition. If you give me some terms as I of arity xi, yi, where I is an finite set, and T, which has arity sum of xi, sum of yi, y, then I get a new term T of S1, Sn, let's say, of arity what it needs to be. So this generalizes superposition. And finally, there is a rule that makes sense if you want only in the enriched setting, which is this. If T is a term, is a xyi term, and Z is another arity, then I also get a term T to the Z, which is now as arity this way. So this is kind of encoding the monadal structure into the notion of term. I should not actually say that for what we do, I mean, to characterize the theorem, it's actually enough to consider Z in a generator of V. Which means if V is set, 1 is a generator, so this is a trivial rule. And so in many other examples like posets, metric spaces, or billiard loops. Okay, and so these are my terms. You start from these two, and then you apply these rules, and that gets recursively your class of terms. And hopefully you can see how to interpret them given a structure. I've just changed the notation for the category, but doesn't matter too much. So given a structure L, this is interpreted by just taking decomposition. This guy is just interpreted with as part of the structure. This is interpreted by taking products of the interpretations and then applying. It's very easy. And this is interpreted by taking the power of the interpretation. So there is a very simple way to interpret the terms in a given structure. And I should say, not only in V, but also if you define the structure in any other V category, also the interpretation is done in this way. Okay, so we have terms. That means that we also have equations. So a class of equation will be a collection of things like this, which have the same arity, and we will say that a structure satisfies it if the two interpreted morphisms are the same. And so what we do is, with this notion of term, we can fill the blank spot and write not E for E as above, let's say. And so what this says is that these recursively generated terms in some sense are flexible enough, general enough, to allow you to characterize these purely enriched notions, still with certain elementary rules based on sets and recursively generated fields. Okay, so that's the main theorem, and I will spend the last minutes of this just to give you certain examples and to see what happens when you fix a certain base of enrichment. I don't know what I should erase. Is there actually something to erase? Oh yeah, okay. It's going very well. Okay, so let's start by considering when we do enrichment over posets and over metric spaces to compare it with works in the literature. So if V is poset, so partially ordered sets with order presenting maps with a Cartesian structure, there are works started by, let's see if I remember the list, Adam, Ford, Mills, and Schroeder, where they consider the ordinary notion of term, and between terms, they also allow inequalities to beside standard equalities. And this is captured in our context by taking terms of arity, let's say x2, where 2 is the chain with 2 elements. Because the interpretation of such a thing is something like this, where this is the subposet of A times A given by all pairs where A is less than equal to B. So you can see how writing something like this could correspond to taking a term this and taking the two projections now. And similarly, if one takes metric spaces, and now one needs to go to the locally counter-representable categories because finite metric spaces are very bad in some sense. Again, Adam and Bolzano value introduce certain universal algebra where now one can consider beside usual equations also equations up to epsilon, meaning that the distance between the outputs is less or equal to epsilon. And with a similar trick, we can see them as our terms with an output arity 2 epsilon, that's not epsilon, 2 epsilon, where, as you can guess, that's the metric spaces with 2 points of distance epsilon. So there is a correspondence with some work in the literature, and I will finish just by saying something that hopefully justifies why we are considering this rule and the first rule. Let's take a very simple case of enrichment, abelian groups. Okay, so what happens first of all with the arities? The arities are finitely presented abelian groups, and they are directed sums. Directed sums of things like this, where I am allowing n to be also 0, so that I don't have to denote z separately. And since finite direct sums are very nice, function symbols can just be something like this. So this is Rn. So you can get rid of all the sums when declaring function symbols. And terms are built, if you want, considering arities, that you have these non-trivial arities, are built like classical terms. But in addition, we have addition. So that if you have two terms T and S of the same arity, you have T plus S, and similarly you can also take the opposite as well as multiplication, which is a consequence. And why is that? Because we are allowing these guys here, so we can multiply it out using the structure of this. So in some sense, having rule 1 encodes the theory of V into the notion of terms. And finally, very quickly, if instead we take graded abelian groups or DGR, these guys here become quite important. So a generator of this is given by all the suspensions of the unit. So like Z in degree n and 0 everywhere else. So we cannot get rid of this rule because the unit is not a generator. But this rule becomes actually useful because it is telling you that if you have a term, then you can build the suspension of that term, where the interpretation of this will be given by the suspension of the interpretation. And these are actually needed, so you can't prove the theorem this way without those. Okay, and I think this is all I wanted to say, so thank you very much.
Thank you. Are there questions or comments, please?
So, thanks for the talk. So, I'm interested in operates, and in operates, you have this connection in the non-enriched setting, the models. You also have a very natural notion of enriched operates in a linear PG or any setting. So, does that then fit in the monads that they produce in this?
I actually don't know, so I know very little about that, so, but happy to check. So yeah, if I find more application, I'll be glad to.
Yeah.
I am slightly confused by you are speaking about monads, but you didn't say that they are enriched.
Yes, they are enriched. So yeah.
But isn't that the result that the varieties in the possible case are just the strongly finitary monads, and you have a general theorem in which they are just finitary monads, so I'm confused.
Yeah, okay, so I thought you had also the finitary case.
But then the operations are monotone.
Yeah, okay, so my case is the finitary one.
So you don't assume the operations to be monotone.
Yeah, so I mean, by operation you mean the rules that generate terms. Or what do you mean?
Well, let's take a very simple case.
Yeah.
One unary operation.
Yes. Yeah, that will preserve the order. Yeah.
But then the theorem can't be true.
What? Okay, now
if you only have these operations that preserve order, then the monad is always strongly finitary.
Yeah.
So I'm really surprised that in the theorem.
Maybe we are interpreting them in different ways. I'm happy to talk more about it. Yeah.
I'm wondering, have you developed a logic and thought about the soundness and completeness to kind of have the first part of it, the terms and equations?
Yes and no. The plan is to do more than this. So recently with Rosicki we also have a paper about the enriched regular fragment of this. But yeah, so far we are just looking at models, but at some point we will also look at soundness and completeness and the usual like deduction rules and so on. But yeah, so in the future.
Okay.
I wonder, Lauvier theory is category with finite product
Yeah.
generated by one object.
Yes.
So, is there a description of what is an enriched Liouville theory of the same kind? Because what you're describing is collections of symbols and generations and axioms or whatever. But what would be the conceptual description of what is an enriched Liouville theory?
So yeah, that's what Bauer did. So it's like a category T with finite powers, a V category, sorry, together with a bijective object factor from VF, V factor. So everything I say is enriched, and this is still generated by one object. So everything here is the power of one object by a finitely presentable object of V.
And the finite powers are like cotensor type of structure.
Yeah, so cotensor, yeah, that's another one.
What with by exponent finitely presented exponent.
Yeah, yeah.
And that's it.
That's it, yeah.
Okay. Thank you.
So, category theory is good for generalizing to more complicated cases by hiding the additional generality in the substructure. So I'm wondering, taking your category L to be more complicated things, whether you can handle some dependent type theory, and in connection with that, your clause 3 for L terms looks rather naive. It looks
Yes. Yes. So okay.
rather too much the original case.
Yeah. So the thing is, well, about the first, I hope it will cover some multiple type related stuff. Kind of looking into it. About this, yes, it's kind of naive in some sense, but it's also the best we could do so far because, well, the idea is, I did write a weird why, is that you could replace this with some other notion like other coordinates or something more complicated. But if you do that, your interpretation is not always defined, so you need to define a notion of partial interpretation, and that's something else I'm thinking about. So this is the best we can do with always keeping always defined notion of interpretation.
Richard?
So if you look at post sets and metric spaces,
Yeah.
so they've got a strong generator given by those things there, but they also just have a generator given by 1.
Yes.
So in that case, you can say that you just have ordinary operations plus some assertions of certain kinds related to, like, well, I looked at FE from 1 plus 1 into 2.
Yeah. So that's kind of the way in which I'm thinking of generalizing this group. You start only with output arrays which are in a generator, so 1 for process and so on. And then when you do replacement, you consider F and so. So like in the post-set metric space case, we kind of use these arrays in the language. So they are part of the structure. While when you do equations, then it's enough to consider just things with output array, which the secret.
Okay, I think we have to move to the next talk, so I suggest to postpone the other questions for lunchtime. Thank you.